Let's take a look at an important theorem involving derivatives called the mean value theorem. The mean value theorem, often called MVT, the mean value theorem. And it's a more general version of Rolle's theorem. It's a more general version of Rolle's theorem. You only have to have two hypotheses for the mean value theorem as opposed to three. So it starts the same way as Rolle's theorem. It says, suppose F satisfies, sorry, my microphone cord is getting tangled up, the following two hypotheses. The first one is the same as Rolle's theorem. See if you remember that hypothesis, the most basic hypothesis in calculus, that F is continuous on some closed interval from A to B. And the second hypothesis also matches Rolle's theorem, that F is differentiable on the open interval from A to B. Okay? So we have a function that satisfies both of those conditions. Rolle's theorem has a third hypothesis that f of A equals f of B. We don't need that for the mean value theorem. So if we were to draw a picture of what's going on here, here's A, here's B. Continuous means I have to have a graph that runs from A to B without any gaps or breaks. So maybe it does something like this. Okay? All right. So that's a continuous function, and differentiable means it has to be smooth. There's no jumps, there's no sharp points, there's no vertical tangent lines either. Okay? So that function f satisfies both hypotheses of the mean value theorem, and you can see that the left endpoint does not have the same y value as the right endpoint, as we have to assume with Rolle's theorem. Okay? But if you remember Rolle's theorem, when you created a secant line using the endpoints of the function, the secant line was horizontal. And so what you would have is the conclusion of Rolle's theorem would say that there's some point in between A and B where the tangent line is horizontal also. It has to match that secant line. Okay? Now, mean value theorem has that same exact idea. The mean value theorem says this. It says, then there is a C in the open interval such that, and with Rolle's theorem you would say, well, the derivative at that C value would equal 0, because on Rolle's theorem your secant line has a slope of 0. Here it doesn't. But f prime of C still equals the slope of this secant line, which could be anything now because there's no condition on the endpoints of the interval. So we need to come over here and figure out the slope of this secant line, and that's what the derivative will equal. Okay? So the slope of this secant line is rise over run. So if I were to come over here and make a y-axis, I could label this y value as f of A and this y value as f of B. And the slope of this secant line would be rise over run. So my rise would be the difference in my y values. So that would be f of B minus f of A. That's the vertical change between the beginning and end point, the left endpoint and the right endpoint of my interval. So that's my rise. Divided by my run would be my horizontal measurement, which would be B minus A. And that's the slope of, let's write it this way, that's the slope of the secant line. Okay? That's M with a subscript of the abbreviation secant, SEC. The slope of the secant line can always be calculated like this if your x values are A and B for your interval. Now, in Rolle's theorem, it's very nice because the slope of the secant line is just 0. Okay? So we could conclude in Rolle's theorem that f prime of c would also equal 0. Here, the slope of that secant line could be anything. So, in this case, we can conclude that the tangent line slope at c will equal the secant line slope over that interval. Now, it can be a nightmare to memorize this, so just to understand what's happening. You know how to calculate slope. This is y value minus y value divided by x value minus x value. Rise over run, okay? So that's what the mean value theorem guarantees. Now, what is going on with the c in this picture now? So what this guarantees is that someplace between a and b, we're going to have a tangent line slope to the curve that equals the slope of this line. So you might see maybe like right there, the tangent line slope looks like that approximately, right? And so you can see that that tangent line slope should be equal to the secant line slope. They've got the same slant. And so the location of that point would be the c value that we're talking about. Okay? So whereas in Rolle's theorem, both of these lines would be horizontal, in the mean value theorem, they both just have the same slope, which may not be horizontal. And you can have more than one c value, but I don't see any others in this particular function where the tangent line slope equals the secant line slope. Okay, but that's an illustration of the mean value theorem. Very similar to Rolle's theorem. It's a bit more general though. We don't have to assume that the endpoints have the same height. Okay, let's do an example where we practice applying the hypotheses and the conclusion of the mean value theorem. So let's see. Let's show that. Let's show that f of x equals 1 over x satisfies the hypotheses of the MVT, mean value theorem, satisfies the hypotheses of the MVT on the interval, let's say the closed interval from 1 to 3. Okay, so we'll start with that. We'll show that this particular function satisfies both hypotheses of the mean value theorem on this closed interval. And then you can imagine if we satisfy both hypotheses, we're allowed to make the conclusion of the mean value theorem. So then we'll show that, or we'll find all the c values in the open interval from 1 to 3 that satisfy the conclusion of the MVT. All right? So here we go. If you watch my Rolle's theorem video, we did an example very similar to this. So let's look at hypothesis 1. Let's look at hypothesis 1. Hypothesis 1 says that f needs to be continuous on the closed interval. So in this case, from 1 to 3. Okay? So we need to show that that's true. Well, f of x, very simple function, 1 over x, is continuous on its domain, right? It's a rational function. It's continuous on its domain. It's continuous everywhere it's defined. And this function is not defined at 0, okay? So it's continuous on its domain, which is, if we write it in interval notation, it's everything up to 0 union everything after 0, okay? And this interval, negative infinity to 0 union 0 to infinity, includes all the numbers inclusively from 1 to 3. So thus, f is continuous on this smaller interval from 1 to 3. Okay? So we've shown that it satisfies hypothesis 1. It's continuous on the closed interval. Now let's look at hypothesis 2, which shows where it's differentiable. Hypothesis 2 says that f is differentiable on the open interval from 1 to 3. Okay? So if I want to know where f is differentiable, I should probably differentiate the function. So let's look at f prime. Sorry, might be easier if I restate what f of x is. F of x is 1 over x, which if I want to differentiate that, would be easier to call it x to the negative first power. Okay, so I'm just rethinking how I look at f of x so that I don't have to do the quotient rule. Now I can just do the power rule. So f prime of x equals negative 1, or just negative, x to the negative 2, which is negative 1 over x squared. F prime of x exists as long as x does not equal 0. So f prime of x equals negative 1 over x squared, which exists when x does not equal 0. Since 0 is not in this open interval, right, we know that f prime of x exists on this open interval because it only doesn't exist if x is 0. So thus, you could say f prime exists on that interval. Let's say that. F prime exists on the open interval from 1 to 3. Implying if f prime exists, then that means f is differentiable. Implying that f is differentiable on that open interval from 1 to 3. And that's what we needed to show for our hypothesis 2. So again, look at the derivative, figure out where it exists. Then that's where the function is differentiable. And in this case, it's differentiable from 1 to 3. So we've satisfied hypothesis 2, and we've finished the first part of the problem. Okay? We've shown that the function satisfies both hypotheses of the mean value theorem. Now what we need to do, since it satisfies both hypotheses, we know for a fact that it satisfies the conclusion, meaning that we can find a c between a and b such that the derivative of the function equals the slope of the secant line. Okay? Let's see here. Trying to find a marker that works fine. I think we'll stick with let's go with purple. I think the purple is working okay. So now we need to find all the c's that satisfy the conclusion. So it'd be handy to restate the conclusion. The conclusion says there exists a c in the open interval such that f prime of c equals the slope of the secant line, which in this case would be f of 3, the y value at 3, minus f of 1, the y value at 1, over the x value 3 minus the x value 1. Okay? All right. So what we'll do is we're going to look at f prime of x, and we're going to look at this number, and then we're going to set those equal to each other to find out what x values work. So here we go. We already saw that f prime of x equals negative 1 over x squared. Okay, so we did that before, just recalling that. That's the left side of the equation. Instead of c, I'm using x just to get the formula for the derivative. F prime of x equals negative 1 over x squared. And then the slope of the secant line, so we'll do that separately. That equals, well, f of 3 is 1 over 3, minus f of 1 is 1 over 1, which is 1, over 3 minus 1 is 2. Okay? So what is the slope of the secant line? Let's simplify this. 1/3 minus 1 is negative 2/3. Divided by 2 is negative 1/3. Okay? So now what I need to do is I need to figure out when the derivative equals this. When my tangent line slope, I need to find the x values, where my tangent line slope equals my secant line slope on this interval. Okay? So I'm going to set those two things equal to each other and solve for x. So what we're looking for is we want to find x's in the interval from 1 to 3 where negative 1 over x squared equals negative 1/3. Okay? So we're going to solve this equation for x. The first thing I would do is multiply both sides by negative 1 to get rid of the negatives. Okay? The next thing, there's lots of ways to handle this, but the next thing I would do is take the reciprocal of both sides, which turns this into x squared and turns that into 3. And then taking the square root of both sides, I get plus or minus the square root of 3. Now, what we're trying to do, we found the x values where the tangent line slope is the same as the secant line slope. Okay? However, I want to find all of them that are between 1 and 3. So we need to pick the positive square root of 3 because that's between 1 and 3. The negative square root of 3 is not. So c equals the square root of 3 is in this open interval. And if I look at f prime of c, I know that that's going to equal this secant line slope because I set it up to do so. So if you plug the square root of 3 into the derivative formula, you're going to get negative 1/3. And we already know that the secant line slope is negative 1/3 also. So this is the c value that we're looking for that satisfies the conclusion of the mean value theorem. And we only kept the one c value that was in the open interval that was specified. Okay? So that's an application of the mean value theorem, very similar to Rolle's theorem.